Good. So anything else you would like to discuss regarding yesterday's lecture or anything we have covered so far? Okay. So if not, then well, we finished proving the Tut-Berge theorem. And for the rest of this course, today and next week, our focus is going to be entirely on perfect matchings, which, as I said a few times, is my own area of research. So I'm a bit excited about that. Okay, so let's go to perfect matchings. I just want to give you a brief reminder of things we have proved, uh, things that are going to be important for us. So the main result in perfect matchings is Tut's theorem, right? Which may be very well viewed as a generalization of Hall's theorem. So this is, well, I don't remember the numbers, doesn't matter. I think it's 16.3. Yeah. No, sorry, 16.13. Yeah. Okay. So what that says is that a graph G has a perfect matching if and only if for every single set of vertices, when you delete that set, you look at the number of components with odd vertices, and that has to be less than or equal to the number of vertices you deleted. Right? And we use this to prove Peterson's theorem, which is 16.14, which says that every cubic graph without cut edges is matchable. And just to remind you, we are using the term matchable. G is matchable if G has a perfect matching. Okay? Good. So this is something we have already proved using Tut's theorem, right? Good. And this is interesting, right? Because we really need the property that the graph does not have cut edges. Otherwise, we have counterexamples. Otherwise, there exist counterexamples. Okay, good. So, are there any questions regarding all of this? Right? We have proved all of these things so far. All right. So, turns out much stronger things are actually true for cubic graphs. One of these you'll be proving on the assignment. So let me start with that on the last assignment. So not only is it true that in a cubic graph, every single, in a cubic graph without cut edges, there is a perfect matching. What is also true is that for any single edge of the graph, you can find a perfect matching containing that edge. Okay, so let me maybe, so a graph G, we will call it matching covered if one, the graph is connected, and two, every edge of the graph belongs to some perfect matching. And turns out the following is true. Peterson's theorem strengthening. Every cubic graph And now, from now on, rather than saying without cut edges, I'll just say two edge connected. And in the case of cubic graphs, you have proved on a previous assignment that edge connectivity is the same as vertex connectivity. So I'm just going to call them two connected cubic graphs. Okay. So every two connected cubic graph is matching covered. The proof of this is very similar to uh, Peterson's theorem proof that we covered. And it will be on assignment 5 with some additional hints. Okay, so let's take an example. Let me just draw the Peterson graph. Okay, so in the Peterson graph, you can choose any single edge you like, and you'll be able to find a perfect matching containing that edge. To give you an example, in fact, you know what? Let me just show you all the perfect matchings of the Peterson graph. Let me make two drawings of this and convince you that every single edge belongs to some perfect matcher. So notice that in any perfect matching of the Peterson graph, you will use an odd number of these five edges, the five edges that meet the red circle, right? You will have to use an odd number of these five edges because inside you have an odd number of vertices, outside you have an odd number of vertices. Okay, so then there are two possibilities. For any perfect matching M, if M is a blue colored perfect matching, its intersection with the cut C, so C is red colored edges, right? It has to be 1, 3, or 5, right? It has to be an odd number. Well, you can verify on your own that 3 does not work. There are no such perfect matchings in the graph where G is the Peterson graph. Okay, that you can check on your own. So then there are two possibilities. Either you take one of these edges or you take all five of these edges, right? If you take all five edges, then of course you get the perfect matching, which is all five of these edges, right? Otherwise, you take one of these edges. So let me choose the top edge. And now I cannot take any of these four edges, right? The intersection is exactly 1. So now you can check that the remaining graph has just one perfect matching. You take this edge, and you take these two edges. Okay? So this is a perfect matching where the intersection of M and C is exactly 1, right? And if you rotate this, then you will get 5 perfect matchings, right? The Peterson graph has this rotational symmetry. So if you keep rotating it, you will get 5 different perfect matchings, each one using one of these edges from the cut, right? So there exists 5 such perfect matchings by rotational symmetry. Okay, so that shows you all the 6 perfect matchings of the Peterson graph. Okay, are there any questions regarding what we have done so far?
Sir,
Yeah,
so is the number of perfect matchings generally calculable?
that is a very good point. We are going to come there very soon.
Okay, okay, and
So
how are we like confident that there are
yeah,
no other perfect matchings for the Peterson's graph?
right, right. So in the Peterson graph, do you agree with this statement that in any perfect matching, you will have to use one, three, or five edges from the cut C, which is the five blue edges in this drawing. Do you agree with
Yes,
that?
sir.
You
Yes,
have
sir.
to use an odd number of them. So you can verify on your own that if you choose three edges, then you will not be able to complete it to a perfect matching. So there are basically two cases. Either the three edges are consecutive, or you choose two consecutive edges and you skip one. Okay? So you can take both of those possibilities and see that you will not be able to complete it to a perfect matching. So then your only possibilities are you choose any one of the five edges or you choose all five edges. Okay?
Okay, sir. Yes, sir.
And if you choose any one of those five edges and you don't use the remaining four edges, then you can verify easily by inspection that there is only one way to complete the perfect matching. So you will get five of these perfect matchings and you will get one of this type, right? So in the case of the Peterson graph, it's basically by inspection. So probably you need to make a few drawings and check it, but I'll leave it. I'll leave that to you. Right? So confirm this. I'll leave that as a do-it-yourself exercise, but it's not difficult. It's really just by inspection. Okay. So in the case of Peterson graph, there is exactly six perfect matchings. What about counting the number of perfect matchings? So since you have already asked me, let me tell you, unless P is equal to NP, which people believe is not true, there is no polynomial time algorithm, or if you like, efficient algorithm to compute the number of perfect matchings in a graph. Okay, so whether a graph has a perfect matching or not, that is polynomial time doable. There is an algorithm called Edmonds algorithm, which we are not covering in this course. It is in Bondi and Murthy in case you're interested. So using Edmonds algorithm, you can check whether a graph has a perfect matching or not. Okay. However, when it comes to calculating the number of perfect matchings, we don't expect there to be any polynomial time algorithm. Okay, I'll talk a bit more about this later. Okay, good. In fact, so this strengthening is clear, right? We are saying that every single edge belongs to some perfect matchings. So that clearly gives you a lower bound that you have at least as many perfect matchings as actually does it give you a lower bound? It's not clear. It should give us some lower bound. Um, for every single edge, there is a perfect matching. So you can get some linear lower bound using this, I think, if you just work out the math. But what is also true for cubic graphs is that actually cubic graphs have exponentially many perfect matchings. So I will state the exact theorem that was proved just 1 decade ago. So theorem, I myself have never read the proof of this. I haven't yet found the time. Every cubic graph G, two connected cubic graph G has at least 2 to the power number of vertices divided by 3656. I have no idea where they found this number from or how exactly it comes up in their calculations. So that is a theorem that was proved by Esperet and four other authors. I won't write down the names. 2011. Okay, and this was a conjecture of Lowas and Plummer. These authors have written a textbook on matching theory. It's called Matching Theory. Okay, so it was their conjecture from several years ago, and it was proved just in 2011. Okay, so of course, for small cubic graphs, this doesn't mean much, right? Because this quantity is really small for a small cubic graph. But as you increase the number of vertices, it basically is telling you that there's exponentially many perfect matchings in a cubic graph, right? So that kind of makes sense, right? Because if there is exponentially many perfect matchings, how exactly do you count them in polynomial time, right? Any algorithm which is going to list down all the perfect matchings, it's already ruled out, right? That already cannot work in polynomial time because you could have exponentially many perfect matchings um, in the graph, right? So any such algorithm, if it exists, it basically has to avoid listing down all the perfect matchings. It has to find some cleverer way to count the number of perfect matchings in the graph. Okay. So what I wanted to tell you is that cubic graphs in general have much stronger perfect matching related properties. It's not just that they have a perfect matching, they are matching covered, and in fact, they have exponentially many perfect matchings as per this theorem. Okay. Any questions or concerns regarding all of this? Okay, good. So I want to change gears slightly and tell you about a conjecture which is similar to the cycle double cover conjecture. So just to remind you, in the cycle double cover conjecture, what you're doing is you're trying to cover all the edges using cycles. And you can do this for planar graphs, right? We have already proved it for planar graphs. So let me take a planar example just to remind you. If you look at this graph and you take all the faces, all the facial cycles, right? So then what you're doing is you have a collection of cycles. Every edge appears in exactly two cycles, and that's it, right? So the cycle double cover conjecture says that every um, bridgeless graph, oh, sorry, we're not calling them bridges. Every graph without cut edges has a cycle double cover, a collection of cycles such that each edge of the graph appears in precisely two cycles, right? And remember that we are allowing repetition of cycles, repetition of the same cycle, repetition of cycles is allowed. The reason we are allowing this is because otherwise you would have simple counter examples, right? So in a cycle graph, what is a cycle double cover? Well, you take the same cycle twice, right? So this is still a valid cycle double cover. So it turns out there is a similar beautiful conjecture for perfect matchings instead of cycles. It's due to Fulkerson. So what Fulkerson observed, this is conjecture 17.6. So what he conjectured is that every cubic graph, two connected of course, you can cover the edges so that each edge is covered exactly two times by perfect matchings. Okay, and you can do this by just six perfect matchings. So this is the conjecture. Every two connected cubic graph admits a double cover by six perfect matchings. So just to remind you again, double cover. So I want each edge appears in exactly two perfect matchings, and you're allowed to repeat. You're allowed to repeat the same perfect matching. So the six perfect matchings don't have to be distinct. Maybe I'll just say it here. Not necessarily distinct. So the reason Fulkerson came to conjecture has something to do with the perfect matching polytope, which I'm not planning to discuss. So I won't go into the history of this conjecture. But yeah, there was a specific reason due to which he arrived at this conjecture. And just to give you an example, let's go back to the Peterson graph. In the Peterson graph, hopefully I more or less convinced you that there are six perfect matchings. And you can check that every single edge appears in exactly one of these two six perfect matchings. So the Peterson graph satisfies Fulkerson's conjecture, right? Peterson satisfies this, which is good to know because typically when you check a conjecture uh, of this kind, one of the first examples you would check is the Peterson graph, because if there is a counter example, there is a high chance it is the Peterson graph, right? So not in this conjecture, right? So let me already tell you that, well, remember that a cubic graph, there are two possibilities. Either the graph is three edge colorable or it is four edge colorable. Right? Maybe I should be more precise. I should say either chi prime g is equal to 3 or chi prime g is equal to 4. So clearly the conjecture is true for these graphs. Does anybody see why? I claim that the conjecture is true for all these graphs. Whenever the graph is three edge colorable, the conjecture is true. Does anybody see that? If you know that your graph is three edge colorable, it's a two connected cubic graph, it is three edge colorable, can you convince me that the graph has a double cover by six perfect matchings? Let's take a quick example. So here is a graph that is cubic, two connected, and you can color the edges with three colors. Here is one perfect matching. Here is another perfect matching. And here you've got a third perfect matching, red, blue, and green. Okay. So this is a graph that is cubic, two connected, and it's three edge colorable, right? So how would you construct double cover using six perfect matchings for this graph? I've already shown you three perfect matchings. I just want you to construct a double cover. right? So you have three perfect matchings. Every single edge appears in exactly one of these perfect matchings because it is a coloring. The same edge cannot be red and blue at the same time, right? So every single edge is either red, blue, or green. So every edge has been covered exactly once. How would you construct six perfect matchings so that all edges are covered twice? This is easy. Come on.
The like so can you go to the graph?
Yeah.
Like putting the blue on the top and the other, like I mean just interchanging these matchings will give.
Right. So you don't even need to do anything. You can just take each of these perfect matchings twice. Is that what you're saying? So then you will get six perfect matchings, right?
Yes sir, in a
Right.
sense, yes sir.
Right. So M1, M2, M3, and you repeat the three perfect matchings again because remember, we don't need the perfect matchings to be distinct, right? So I'm just going to repeat the same three perfect matchings. And now I have six perfect matchings, not necessarily distinct, but every edge is covered exactly twice, right? So it's clearly true for graphs that are three edge colorable. You just take a three edge coloring, you have three perfect matchings, and you repeat each of them twice. So you will get your six perfect matchings. What is really cool about the conjecture of Fulkerson is that you can also do this for graphs that are not three edge colorable, like the Peterson graph. So even for these graphs, you can find six perfect matchings that will cover all the edges of the graph twice. Every edge will be covered exactly twice. Okay. So, well, this is a conjecture. We don't know how to prove it yet. Um, I think Fulkerson, so that must be from at least 70s or 80s. It can't be much, it can't be more recent than that. There is another related conjecture that I want to mention. So, well, what if you don't care to cover every edge twice? What if you just want to cover all the edges exactly once? Well, then you take Fulkerson's conjectured six perfect matchings and you throw away one of the matchings. If you throw away one of them, you will still cover every edge at least once. So that is another conjecture due to Berge. It's Berge. I think he's French. So there is a weaker conjecture due to Berge. This is 17.7. And he says that every two connected cubic graph admits a covering by five perfect matchings. So here what I mean is that each edge is covered at least once. Okay? Right. So turns out this is best possible because in the case of the Peterson graph, you actually need five perfect matchings. In case of Peterson graph, you can try this on your own. You take your six perfect matchings, throw away two of those perfect matchings, and you will see that some edge is not covered at all. In case of Peterson graph, you need at least five perfect matchings to cover all edges. Okay? So it's clear, right, that this is a weaker conjecture. If Fulkerson's conjecture is true, then you take your six perfect matchings, you throw away one of them, you will still cover every edge at least one time because every edge was covered twice. The converse is not clear. Berge's conjecture does not imply Fulkerson's conjecture. Okay, good. So those are the conjectures I want to tell you about. And for the rest, I want to switch to counting perfect matchings. So let's see if we will be able to cover much. Right. But before we go there, let me just ask you if there are any questions regarding these conjectures. Right, so I wanted to tell you because they are very similar to the cycle double cover conjecture, which we have discussed before. And well, I guess they are quite beautiful. Why would you be able to cover all the edges exactly twice by six perfect matchings? Why is it six? I don't know. Okay. Um, so are there any questions or concerns regarding any of this? Okay, if not, then let's switch to counting perfect matchings. As you've already discussed, unless P equals NP, no polynomial time algorithm. This, I believe, is due to Valiant 1979. We won't be proving this, of course. Um, so in this remaining part of the course, there are a bunch of things that I will not be proving, things that are more algebraic or complexity theoretic. But I will show you structural graph theory type of proofs. Right? I will just skip the uh, other kinds of proofs. We will take certain things for granted. Okay, good. So then what do we do? If we still want to count the number of perfect matchings in a graph, just to let you know, counting perfect matchings turns out to be an important problem in theoretical physics. This is relevant to theoretical physics, where it's called the dimer problem. So you can read about the dimer problem. It's basically counting perfect matchings in a different language. Okay. So physicists in the 1960s were already interested in counting the number of perfect matchings in a graph. It corresponded to the number of molecular arrangements in something blah blah blah. I'm not a physicist, so I don't know much. Okay, so in the 1960s, they were already interested in this problem, and what they realized is that while they did not know how to count the number of perfect matchings in any graph, they realized that in certain types of graphs, you could actually count the number of perfect matchings quite easily. Okay, so they realized that in certain special graphs, counting number of perfect matchings was actually the same as computing a certain determinant. I'll tell you a bit more about these things in detail in the next lecture. And computing determinants is easy, Gaussian elimination. Okay, so this is an easy problem. So because it was the same as computing a determinant, you could count the number of perfect matchings. Okay, and these special graphs are called Pfaffian graphs. I'll give you the rigorous definitions in the next lecture. Right. So whenever you know that a graph is Pfaffian, then you would be able to compute the number of perfect matchings by just computing a determinant. And so you would be able to do it in polynomial time. Okay, so we'll define this later. But before I tell you about Pfaffian graphs and their different definitions, I want to tell you about another kind of graphs, so that we don't have to look at all graphs in the world. We can restrict ourselves to these special graphs. So I'll start with an example. Supposing I give you this graph. I want to count the number of perfect matchings. I claim that there is some edge in this graph that is not in any perfect matching. Can anybody tell me which one is that edge? There is some edge in this graph that does not belong to any perfect matching. Can anybody tell me what is that edge? It's easy to describe. The diagonal one, exactly. So you mean the cut edge. Okay? So, right. So that edge is not in any perfect matching. So what I can do is I can throw away that edge and I can look at the remaining graph. In this graph, which is two connected components, you can check easily that every single edge belongs to some perfect matching. Right? This graph here, this component has two perfect matchings, and this one has three perfect matchings. Either you take the horizontal, or you take the vertical, or you take the diagonal. Okay? So the graph G minus E has six perfect matchings, right? Because it's 2 times 3. What I'm trying to say is that we don't need to look at the original graph. We just need to look at the graph obtained after throwing away all the edges that do not belong to any perfect matching. Because if an edge does not belong to any perfect matching, it does not contribute to the number of perfect matchings. Right? So I can throw away all these edges, and then I can look at the connected components. And these are exactly the matching covered graphs that we already defined a few minutes ago. Right? So in order to count the number of perfect matchings, we may restrict our attention to matching covered graphs. To remind you, it is a connected graph where every edge belongs to a perfect matching. So this is a matching covered graph, G2. This is a matching covered graph, G1, right? So if I can count the number of perfect matchings in matching covered graphs, then I can count the number of perfect matchings for every graph. Okay? You might ask me, how do you check that an edge is in a perfect matching or not? That is easy. You know that checking whether a graph is a perfect matching or not is doable in polynomial time because of Edmond's algorithm, which we did not discuss. Using that as a subroutine, you can check whether any edge belongs to a perfect matching or not. That's quite easy. Okay, so so from now on, for the rest of this course, we will mostly talk about matching covered graphs, right? So we will assume that our graph is connected and every edge belongs to some perfect matching. Okay, so I still need to tell you what Pfaffian graphs are, but since we have we are at the end of the lecture time, we will do that next week. Okay, so next week we will discuss what Pfaffian graphs are. We will restrict ourselves to matching covered graphs. So we will look at Pfaffian matching covered graphs because we don't care for all the graphs in the world. And then we will go into the theory of matching covered graphs and see what all is known about Pfaffian graphs, and we will probably prove some easy results, but most of the results will be fairly difficult that we may not be proving it in the course. But I will give you pointers in case you're interested. And who knows, if we have time, we might prove some of those things. Let's see. Okay, good. Any questions or concerns regarding anything we've discussed so far? Okay, so is everything clear then? Also, on your assignment 4, um, the last problem is related to bipartite matching covered graphs. So I'm going to put some of the theory of matching covered graphs on the assignments 4 and 5, um, so that you can prove things on your own, but I will give you the steps to go through that. Okay. So there will be quite some stuff on matching covered graphs on the last assignment. Okay. All right. So if there are no more questions or concerns, feel free to leave the meeting. I'm still here for another 5 minutes. Okay, maybe I'll stop recording.